Thank you very much. I'm very glad that you like this, and hopefully that gives a good appetizer on what is now to come. So I need to put this back to screen. There you go. And to make sure that everybody on Zoom can see, there you go. Now you should see me. All right. And this should be working. All right. So welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. Today we are going to start a new section. As you saw, tables are back. And I need to tell you a bit of the context of what we are doing. So first, yay, one more step higher. After storage and encoding and syntax, we are now elevating ourselves to data models, but you will see still a bit on the physical level. So as you know, tables are typically used in relational databases, but we saw that these ones have a problem. They are monolithic. It's something you install on one machine, then it's limited, it doesn't parallelize, and so on. We can try to scale up, have more CPU, have more memory, but it costs a lot of money. Engineers try to scale it out at the very beginning, but manually, in the sense that they would install a relational database on many machines, but then they have to deal with all of the complexity of the management and the partitioning, the replication, and so on. So it costs a lot of money, costs a lot of time, and this is why they had to invent something new. So the idea of what we are going to look at today, which is known as HBase, is a white column store. And the idea is that we are going to store tables like these tabular structures on the top of a cluster of machines, just like we've already succeeded with file systems, right? With storing file hierarchies. And so, as you might have guessed, we are going to be using HDFS as our file system beneath HBase. So you see the architecture, how it's working. In the same way that a relational database is using the local file system to store its data, a white column store is going to use a distributed file system to store its data, right? So we build on top of HDFS, and it will be very interesting to understand the abstraction. But of course, since we are just using it as a client of HDFS, it means that we don't really need to care too much about the internals of HDFS. We will in some way when it comes to performance improvements, but for now, you can just assume that HDFS is a hard disk, very large, petabytes of space, and you can store directories and files in huge blocks. Okay, so now I need to tell you why we have a novelty. Why do we have yet another system? Why could we not use the existing systems? And here you see a summary of those that we have seen. So object stores, I mean here S3, Azure Blob Storage, RDBMS, I mean PostgreSQL, for example. HDFS, we've just seen it last week. And then we have key value stores like Dynamo and DynamoDB that is built on top. And you see that they all have drawbacks. For example, if you look at an object store, it's basically, it doesn't have a great latency. It has dozens, hundreds of milliseconds at first. You cannot update any objects. You have to rewrite them completely. You cannot make small updates. And you don't have random access to the objects. That's the same idea as the updates. And then you can not have range access. Range access means an interval of IDs. That we don't have in S3. In a relational database management system, we don't have high throughput in the sense that we can handle terabytes and terabytes of data efficiently. We don't have large collections. It has to fit on a single machine. In HDFS, we don't have low latency. You remember what I told you, if you type something on the command line to see a file, it's 1 or 2 seconds of delay. You cannot have any updates to HDFS files. You can only append at the end, that's all. And you don't have random access in HDFS. I mean, you do have it if you want, but it's going to be so slow that practically you don't have random access. And in key value stores, we don't have high throughput because these are very small values of 400 kilobytes at most every time. We don't have large values. 400 kilobytes is the limit. And we don't have range access. In Dynamo, you can ask for a specific key, but you cannot ask for an interval of keys, right? Who is with me? Who would like to have a system that has all of that? Well, here you go. We are going to build a system that has all of that. Can you imagine high throughput, low latency, updates, large values, large collections, random access, range access, everything. So this is what we are building now. And in order to start, I will follow the same methods that I had with HDFS. If you remember, that was 2 weeks ago. I started with the logical model. Remember, files and directories, and then we have the files divided in blocks, right? That was the logical model. And then I explained the architecture, the internals of HDFS with the name node, the data nodes, and so on. Who remembers this? Right, awesome. So now I'm going to do the same thing. I'm going to start with the logical model of a white column store, in specifically HBase, and then we'll go into the architecture. Just so you have an early warning, this is probably the most complex lecture of the entire semester, I mean, in the physical architecture, so do not be scared if it's a lot to digest. We are going to take the time to go through it. I expect that you will have many questions, and if I don't know some of the answers, I just investigate it offline, yeah, we'll learn about this. All right, who is ready for the logical data model? Okay, then here you go. First, I want to say a few words about the origin of HBase, which actually is a copy, an open source implementation of Google's Bigtable. Whoever heard of that? Google Bigtable? So this was a system, it's already 20 years old, that is proprietary. And so just like GFS was proprietary, Bigtable as well. And so Hadoop re-implements them in an open source fashion. So the design goal of these systems is that since we want to scan the data, analyze the data, aggregate the data, it's nice if we can avoid joins. So we need to store together what is accessed together. For example, if you have to join two tables, this is what it looks like. You see the spaghetti in the middle between the two tables. That is a join. It's expensive. Small parenthesis, you can actually implement joins in linear times if it's an equality operator, but still there's a constant factor to that. But anyway, if we want to avoid the join, what can we do? Exactly, so we store them together, and what is it called when you store them together, when you pre-compute the join? Denormalize. Do you want to say this as well? Yeah, awesome. So yes, denormalization, right? We denormalize, and this is what we get, right? So here, it looks like it's denormalized all the way, but still in the first normal form. Don't worry, we'll also denormalize past the first normal form. I'll soon explain how that actually is the case. But it means that in Bigtable, the table that we store is actually a huge table that is denormalized, right? So there's not multiple, well, you can have multiple tables, but the spirit is you look at one big table, you don't join anything. Okay, so that is the idea, and that's why it's called Bigtable. That has to do with the fact that because of the denormalization, it does a lot of things. So now the logical model says that every row in the table has a row ID, right? A row ID is just some binary value, right? In fact, you will see in HBase, everything is a binary value. We don't have any types or anything. So a row ID is just a few bytes, and that means that we follow the key value model where every row is a value and the key associated to that value is the row ID, right? Who is with me? It's pretty simple, right? In fact, it looks almost like a key value store at that point, or even an object store. What else can I say? On the row IDs, yes, it does mean that it forces you to have the row ID as a primary key. You cannot change that. It is the row ID column. There was a raised hand over there. Do you still have a raised hand? The raised hand is no longer raised. Okay, so don't hesitate if you have questions. Also on Zoom, you can interrupt. So we have the row ID that uniquely identifies a row. In other words, the row ID is a primary key in that logical table. All right. Oh, I should also say that these row IDs, you might have noticed, they are sorted. See? 0, 0, 0, 1, 2, 4, they are sorted. Now you see the notion of range that starts appearing, right? So there is a sorting. It's not like the key value stores where you have the hash function that shuffles them all around in the ring, so there is no order anymore, right? The order is lost. But here we do have an order, and it is part of the logical data model. Okay, so these are the rows. Now let's go to the columns. It's a very, very, very big table, has a lot of columns. And just like with 8 billion plus human beings, first names are not enough. We also need to disambiguate with last names, middle names. Of course, that depends on the specifics of every country. But basically, we have families. And here is the same. We also have families of columns. So this is why I'm showing the columns in different colors, the purple family, the yellow family, the red family. So they have a family name. That family name is, guess what? A binary value, again, right? Everything is a binary value. So a sequence of bytes. All right, but with colors, it makes it more understandable. So purple, yellow, red. These are called column families. And within the column family, I have names of column. It's like the first name of the column. So here I have, sorry, A and B for the purple family. I'm using uppercase letters, Indo-Arabic numerals for the yellow family, 1 and 2, and then Roman numerals for the red family. These are just examples, because guess what? The column names are also binary values, exactly. They are also sorted, but that will be on the physical level that they are also sorted. There's no notion of sorting on the logical level. So yes, there are binary values as well, right? Sequences of bytes. So far, so good? Everybody with me? Right? It's still rather simple, right? The one thing that might be new from relational databases is the families of columns. This is something we didn't have in a relational database. Okay, and what's really nice about these systems is that we can make up and create new columns on the fly just like that. Well, now you're going to tell me we can also do that in PostgreSQL, right? You can just say alter table, add column, blah, blah, blah. Yes, but that's going to take a while to do it. If you already have a table with billions of records and you want to add a column, you'll have to wait until the columns are added, because it needs to modify the layout on disk. And you might know that in a relational database management system, typically the layout on disk is row-based. It means you have one record, one record, one record. And if you want to add a column, you need to expand the records, right? So you have to rewrite everything. You could imagine, of course, optimizations, but in the native way, that takes a while to add a column. Also, when you add a column, you need to add a column to every record. In HBase, the trick is that when we add a column, what we actually do is we add the column to one record, and all the rest is implicitly having that column as well, but it's not actually physically there. It's just logically there. So you might have, for example, imagine that here I'm saying on that row, I add a new value with a column C. It's going to add the value just for that record, but on the logical level, that also implicitly means there is a column C. It's just empty for the rest. It does mean that it is very sparse, right? So typically a table here is going to be very sparse with a lot of values that are missing, lots of rows, lots of columns, and lots of missing values. Who is with me? Right? Okay, so we can add the column names within the column families on the fly very efficiently. It natively supports that. The column families, however, you can also add them, but it takes a bit more time because adding a column family is more heavy, right, in terms of what needs to be done. But the column names within a family, very efficiently, you can add them. Okay, look, I see a raise hands, yes? Wait. We can try to, in small hops to not surprise anybody? Yes? Yeah, go ahead. Okay, we're listening.
When the columns are added on demand, is the space already reserved on the disk, or is it like on-demand sort of space allocation?
On demand means that on the logical level, you add the column, but we'll see that physically, actually, it doesn't do much. Physically, it's only going to add that column for the specific record or the few records for which you did that.
Okay, and when you store like in PostgreSQL, the storage is like on a row basis. So does that mean that in here, like in HBase, the storage is actually columnar, so it's like a column major format?
Almost, yes. So that's you have exactly the right thinking. So I'll say a few words about row storage and column storage. It is the right thinking. In fact, we'll see that the storage in HBase is even at the value level, at the cell level. And that's what makes it so efficient, plus a bit at the family level. But that's exactly the right thinking. It is indeed the case that the reason why adding a column to a relational database management system is inefficient is because the physical storage on disk is based on rows. It's record 1, record 2, record 3, record 4, and that's inefficient. Who sees that?
She has a question.
Right? So I see one raised hand here, another raised hand. I'm just indexing the raised hands to follow. There was another one?
Right here.
Yes, okay. So did I answer your question? Okay, so we'll go for you and then I'll go there.
Does the column families allow us to have the same name for two columns in different families?
Yes. Yep, it is absolutely allowed. That's fine. It's like you can have several people with the same first name. That's totally fine. You can even have people with the same first and last name, but of course, that's where the analogy stops with the real world. Yes, over there.
Yeah, just on the physical level, let's say I add, in our example, I add column C only for the third row. And what happens if I add, let's say, column D, but only for the second row? How does it manage, how does it work for the whole system to know that we actually added the fourth column for this exact row and the third column is basically empty?
Mm-hmm. So first, a remark, you're already speaking about the physical level, which is great because you're already anticipating. Now it's just the logical level. But still, I'm happy to already answer these things. But you're already thinking ahead, basically. Logically, whenever you add a new value for a new column to a new record, logically, the column is there. That's the logical level. On disk, physically, what's going to happen is just that you create a new value that you've just added just for the specific records where you have added it. So in that case, you would create a new value for column C in row number 3 and a new value for column D in row number 2. Physically, that's all that happens. But logically, you have 2 more columns in there, right? Now, when you query the system, probably asking for all the columns that exist might be at first not very efficient because you need a full scan to know all the columns. You could imagine, I don't know if HBase does that, but you could also index, keep an index of all the columns that exist to accelerate that. But typically, a more typical query in HBase is that you ask for specific columns for specific rows, right? And then it just fetches whatever you want to fetch in there, right? Did I answer your question?
Yep.
Right. All right. So any more questions that remains? Any raised hands? No raised hands. Any on Zoom? Any questions on Zoom? We'll quickly look. No, not on Zoom. Okay. Yeah, my screen is a mess over there. All right. Awesome. But I still continue to talk about row storage and column storage because you actually raised an interesting point, and I'd like to take the time to explain that. So. I already told you that a drawback of row storage is when you add a column, it takes time because you need to relocate all of the records. You need to rewrite everything. But there is another drawback of row storage is that imagine as an example, you have a table that has 10 columns, let's say 10 columns, and you have a query that only reads 2 of the columns. Who sees that reading from disk is going to be very inefficient. Even though you touch only 2 columns, you practically have to read everything. Who sees that? Right, great. The idea is that since it's record by record, you need to look at the 2 columns of a record, the 2 columns of a record, the 2 columns of a record, but practically you need to read everything because of the block structure of the disk, right? You cannot just read just specifically the 2 columns because it's likely to be much less than the 4 kilobytes of a block, right? Who sees that? Right, so very inefficient for projection. It's in fact projection, if you want to specifically read specific columns. Which is why, at some point, some people had a brilliant idea, and that was even before these technologies here, before HBase, before white column stores. They had the idea of implementing a relational database management system, same logical model as PostgreSQL, but they just use a column storage on disk. Data independence at work here. Data independence because they just changed the physical storage. Do you see that now, if I store the data in my table, column 1, then column 2, then column 3, then column 4, and I only want to access 2 of the columns, now it's going to be very efficient. Who sees that? Right? Very good. So this is how column storage was invented. And again, that's yet another one of these expressions that was a buzzword for a few years where everybody was suddenly researching column storage. Column storage, though, is only an intermediate idea because we are not in wide column stores yet. There's no notion of column family. It's just the idea that we physically store them column by column rather than row by row. Okay? So parenthesis closed, but now you have this concept of row storage and column storage, even for a monolithic relational database. Okay. And by the way, I could add that if you have column storage, then adding a new column is also easier to do because you just need to write a new zone with the new column and that's it, right? All the other columns, they stay where they are, right? Who sees that as well, right? All right, so that's the benefits of column storage. And I'm starting with that because this idea of accessing only the data you need from the disk to accelerate the query is something we'll see again and again and again. That's called the push down. We push down a projection basically to only read the data we need. But back to where we were, we can add columns on the fly. I'm repeating something that I've already told you now that everything is a sequence of bytes. The row IDs are sequences of bytes. The column families are sequences of bytes. The column names are sequences of bytes. So at first, it sounds a bit scary because it looks like all the burden goes to the user to figure out what to put in there. But don't worry, because as you can imagine, there are libraries that are built on top of these systems. And these libraries will provide some wrappers that allow you to see integers and strings and all kinds of things. And the library is going to take care of putting them as binary values, right? It's again an architecture with multiple layers. Okay? But the fact that everything is a sequence of bytes, for the physical level, it makes it a bit easier. Okay. One more thing I need to say, and that is a difference with the relational databases, at least let's say the classical ones, is that the values in there, they don't really need to be atomic in the sense of the first normal form. You could have big cells containing, for example, JSON documents or XML documents. They're back also, XML and JSON documents. So you could absolutely use that kind of a system to store JSON documents, XML documents, and even HTML documents. And in fact, the companies like Google, Yahoo, and so on, they do store HTML pages in there. You can build an index of the internet in that kind of structure and store the HTML pages as values, right? Who is with me, right? Who agrees we are not even in the first normal form then, right? Okay. But again, from the perspective of the system, everything is a sequence of bytes, including the value. So we don't even know at that level that it's XML or JSON. There was a question.
We have a question over there.
I don't see. Well, I'll follow the mic, and then I'll see who this is. Oh, over there. Okay.
You said cells can store entire JSON documents, but does the table, whole column storage system also need to be in JSON or not?
No, the entire system, we'll see later how it's physically stored, but it is not stored as JSON. It's really stored also in binary data. We'll see exactly the details of that. These are called H files, and we'll see what there is inside.
So you can have cells with JSON, with HTML, with...
Exactly. You can store, as a user, you can decide to store JSON documents or XML documents, right? So basically, compared to that system, you have to see XML and JSON and HTML as being above the system, not below, right? So we store XML, JSON, HTML in HBase, not the opposites, right? Does it answer your question? Yeah, awesome. So you can see it's a very physical system. That's what it means. It's low level. We'll see there's not even SQL or that kind of language at top, at least not in the native version. Any other questions? Don't see any raised hands, also not on Zoom. All right. But there is still a design limit. It's not a hard limit, but it's a design limit, is that you should avoid more than 10 megabytes, right? You can put bigger and bigger and bigger values like JSON, XML, but try to not exceed 10 megabytes, because otherwise it will work, but then the system is going to be outside of what it was designed for, and then things might become very slow, right? So all the way to 10 megabytes. And yes, this is a new order of magnitudes that I haven't mentioned before. Let's recap on the order of magnitudes, by the way, that we've seen so far. We've seen the order of magnitude of a block on your laptop, 4 kilobytes, right? Remember that one? It's also the order of magnitude of the pages in page blobs in Azure. This order of magnitude allows you random access, because writing 4 kilobytes of data is almost instant, right? So you have random access to your data. So 4 kilobytes, that's the order of magnitude. There is also, of course, the smaller order of magnitude of a single value, which is typically a few bytes if it's an atomic value, but this one is more on the logical level. So a value of few bytes, a block on your laptop's hard drive, 4 kilobytes. Now we have this new order of magnitudes of around 10 megabytes, 16 megabytes, that will be the typical order of magnitude for documents, XML, JSON, and so on. We'll also see, who knows MongoDB? Right? We'll see it in a few weeks. This is also the order of magnitude of the maximum size of a document in MongoDB. So you can put that order of magnitude in your mind as an additional order of magnitude. This is the typical maximum size of an individual document, like JSON or XML, right, or HTML. And this is what HBase is designed for storing. It doesn't mean, you shouldn't imagine that all the tables all have cells with 10 megabytes inside. You can also have a lot of cells with very few bytes, right? That's totally fine, just like values like you would have in PostgreSQL. But you can also store this kind of large values. Okay. So this is the logical data model. Now, I'm going to tell you what we can do with it, also on the logical level. What can users do to interact with HBase? So first, they can get something. That shouldn't be a surprise. You can also get an object in S3. You can get a value in a key value store. You can get a file or a block in HDFS. Well, you can also get what there is on a row. You can specify a row ID, and then you say, get me the values on that row ID, right? You can also, I don't have the slide for that. In your get, you can also specify if you only want some families. You might say, I want everything for that row ID, then everything that is marked in red here would be returned. But you can also say, I'm only interested in the purple values for that row ID. Then you would only return the part, in that case, that would be right here, right? Or you can say, I want the purple and the yellow, and then you just return that, but you do not return that. Do you see that it's very efficient because we will store the families separately? So it's going to be efficient to access just the ones we need, right? Okay, so this is for getting a value. By now, you probably realize that it's low level, because I'm not talking about projections or selections or group by or order by like you would in a high-level query language. We are at the physical level of get, put, delete, these kind of things, right? So very low level compared to a query language. All right. Then we have put. Put means that you can create a new row with a specific row ID, or you can also put some new values, some different values in an existing row. You can write a full row, you can write only some column families, you can write only some values, but basically you create or update the data. But you see it's more granular than a key value store or an object store, because we can also manipulate some of the cells, but not the entire row, right? So you see we have a bit more granularity than we have in S3 or in Dynamo, right? All right, so we can put some values in there. We can scan. Now that is new, and that has to do with the range queries that I told you about, that S3 does not support ranges. You cannot say, I want this interval of object IDs. That doesn't exist. In Dynamo, you can also not do that. You cannot have an interval of keys. Why? Because the keys are shuffled by the hash function all over the ring. So there is no efficient way of retrieving an interval of keys. Who sees that? Right? Okay. But in HBase, we do efficiently handle the sorted row IDs. So I can run a scan over my table. I can, of course, only specify specific column families to scan, just like for get and put. And I can also specify a specific interval. I don't have a slide for that, but you can also just say you want to scan between here and here, right? And you just scan like this, okay? So that allows you to run a scan and either execute something or have an iteration over the values. You can even do the scans in parallel, as we'll see in a few weeks, right? You have one computer that scans the first 10%, another computer that scans the next 20%, all in parallel, right? So this is a scan. That's the third one, new to HBase. We haven't seen scans so far. And the last one, can you, oh, that's actually an example of a scan. I did have a slide. Sorry, it's just that it was so light, the pink here, that I didn't realize. But this is a picture of a scan specific to a specific row ID interval and a specific column family right there. Can you guess what the fourth one is? Then I'll come to you. What's the fourth one? Get, put, scan, and? Delete, exactly, you're absolutely right. There was a question, yes, over there. Yeah, you have to be very, very, very careful with, that's why I'm saying very small, small hops. Yeah, all right, go ahead. Are you okay? Yeah, all good, yeah, go ahead.
I'm confused because I think I remember the random access property to say that you can actually change any part of the file or of the object anywhere.
Yep.
And then you said that you can't, like, this is more granular because you, in HBase, you can actually change only parts of the row.
Yes.
So what's the difference between the random access property and which of the other systems have random access and why is HBase better?
So random access basically means that it's very efficient at repeatedly access very small parts of the system, right? That's what it means, either read or write, right? So imagine you have a file that is 1 gigabyte, and you can specifically read 10 bytes in the file or even replace 10 bytes, right? The reason why on your laptop you can do it, it's because the blocks are just 4 kilobytes. So whenever you want to modify something, you just rewrite the 4 kilobyte block corresponding to that. And the reason it gives you random access is that it's so fast to do, so efficient, that as a user, you can just keep doing that all the time and it's fast. You don't see any problem. The reason why I'm saying that HDFS doesn't have random access is that if you would try to do this, in HDFS, you say, okay, I just want to read 10 bytes of that block here and 10 bytes of that block there and do it repeatedly, then you will see it's extremely slow. The reason why it's slow is the latency every time you try to access one of these blocks, because they're also 128 megabytes, right? You would have to rewrite, if you want to have a random access write, you need to rewrite every time the entire file when you do that. You cannot even overwrite the block. You can append at the end. The only block that can be rewritten is the last block, right? So when you append. But you cannot have random access writes because you need to rewrite the entire file. So imagine a user that wants to 1,000 times modify a small portion of a file. They will be there for days, weeks, or maybe even months until they have done that. But with a system in which you just need to write a small block of your laptop of 4 kilobytes, then you have random access. Right? Does it make sense? So I still have more elements of answer, but at that point, that makes sense, right? Yeah. Then also to answer your question, S3 also does not have random access because you have to write an entire object if you want to modify it. There's only no other solution than to rewrite the entire object. I don't know if Azure Blob Storage would let you modify a single block, but even if it would, it's for 4 gigabytes. So also that would be very inefficient. Azure page blobs have random access because the pages are just 0.5 kilobyte. This is so small that you can write. Did you have a feedback question or maybe, yeah? Did that answer your question? Yeah, awesome, perfect.
We have a question here.
Yeah, let me ask before, who is clear now on random access, why I'm saying we don't have random access on HDFS or S3? Okay, awesome, perfect. Go ahead.
You were talking about scanning for ranges.
About?
Scanning for ranges.
Yes, scanning for ranges.
Right, but here only the green family, one row in the green family is actually sorted, no?
So first, this is sorted. And here I'm taking this range here between 1E0 and 22A. Plus, I'm only asking for the yellow family, right? So it's a double restriction, right? I only need the yellow family and only for that range of row IDs.
So what if I cared for a range of values in the yellow family?
Oh, you mean a range here, a range of columns?
Yeah.
That's actually a good question. So I'm not sure if that's part of the design. You will probably be able to see it also when we look at the physical level, but based on the physical level storage, I think that would not be efficient. Okay. And maybe we can take note of this and come back to it as soon as I've shown you the physical storage to let you see that that wouldn't be efficient to access a range of columns within a family, right? That's your question.
Actually, a range of values within a different column, like the column that is not row ID here. But
so let me try to. So you didn't mean a range of column names?
Well, now we're accessing a range of values in row ID, right?
A range of row IDs. We're accessing a range of row ID for a specific column family.
Exactly. But the only column that is sorted is the green column.
The only column that is. Oh, yes, absolutely. The green column is special. That's the row ID. That's not a column family. That's the row ID.
Okay, and if I wanted a range of, let's say, all the people whose surname starts with A or something, a range like this.
Ah, yes, now I see. You want to have a predicate on the values themselves.
Exactly.
Right. So indeed, this is different. Here, it's only a range of row IDs. I'm only having a range of row IDs. If you want a range of values, that you will have to achieve with a scan. You would have to scan through the data and on the fly use the CPU to filter them. I'm not saying it's inefficient because you can use MapReduce or Spark to do it, but it's not going to be as fast as in a relational database because you would have what in a relational database that does that very efficiently? An index, exactly. You would have an index. HBase doesn't have indices like that. It has indices sort of for the row ID in that sense, that it handled it physically as a first-class citizen, but there are no indices at least natively, right? However, users of HBase could, of course, build their own indices next to HBase, in addition to HBase, and then know what row IDs to look at, right? But that would be outside of HBase. Oh. Did I answer your question?
Yes.
Yeah. All right. Other questions? Yes, over there.
Yeah, maybe sort of extending on his question. Does the row ID have any semantic meaning that's related to the records themselves, or is it just some random unique number?
It's a sequence of bytes. if I'm correct, and I can check, I think the user controls that. So if you want your row ID to be, let's say, a social security number, then you can, right? From the perspective of HBase, it's a sequence of bytes. As the user, you're free to put whatever you want in the row ID. It might have a meaning for you, basically.
Okay, thanks.
Mhm.
A question here.
You said that since we are storing the values in columns, it's very easy to access a subset of the columns, right?
We are storing them in column families.
Oh, yeah.
When I said we store them in column, what I refer to is the column storage of a relational database, what was invented already even before that, right? When people realized that you can rewrite a new version of PostgreSQL, but storing the data column by column. We will see that in the case of HBase, it's called a wide column store. And in a wide column store, it's more precise to say it's a column family storage. It's column family by column family. The order, in fact, in which we will store, if I'm not mistaken, and I can try by memory to do it, it would be basically stored within that family, this one, then 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 this one. Right? So it's by column family, but within the column family, it's not column by column. That's the reason why earlier, when I misunderstood your question, I was saying it's not efficient to have a range of column within a column family.
Okay.
Right.
You said that like if we would like to make a projection, this would be very helpful and very efficient. But if we only would like to access one line, wouldn't it be very bad, very inefficient?
So first on the projection, when I said it's very efficient as projecting, I was also referring to the column storage of a relational database. That's very efficient at projecting. In that case, we would be very efficient if we project to a family, right? An entire family, then it's efficient. But we really have, the difference between column storage and wide column stores is that, just to give you ballpark so that you have visuals in your head, when you have a relational table stored in a column storage, the number of columns is not very large. You might have 10 columns, 20 columns. So typically in the classical systems, 255 is the maximum number of columns. Today, probably no longer, it can be more, but historically 255 was a hard stop for the number of columns. In a wide column store, you could have millions of columns, because it's sparse, right? So you can see, so when I tell you there's billions of rows and millions of columns, you can be wow, that means like quintillion or so many values, but no, it's very sparse. So this is the reason why you can have millions of columns. And because you can have millions of columns, this is why we group them in column families to still have some way to partially project, so to say. Maybe I could say also something else for your intuition about column families. Typically, the column families would correspond to normalized tables before you join. So you can imagine in a relational database system where the data came from before joining, hypothetically, there doesn't have to be one, you would have the purple table, the yellow table, and the red table. They might have been separate tables. And when you join them together, you get these enormous tables, but you still retain the column family grouping that kind of remembers what belongs together. Right? Does it answer your question? All right, so you've deserved a break. I will answer more questions right after the break, and starting with you, and then we'll continue. Thank you.